Part 2, we're on question 10. A researcher claims that dolphins use echolocation sound with a frequency of 1.64 times 10 to the 5 hertz. If the speed of sound in water is 1.53 times 10 to the 3 meters per second, what is the wavelength of the dolphin's sonar? So pretty straightforward question. If you just write down the variables, you'll figure it out pretty quickly. We've been given a frequency. We've been given a velocity. And we're trying to find the wavelength. So it's a universal wavelength question. The velocity divided by the frequency gives you your answer, which you'll get in meters, and then you can convert it to millimeters or centimeters, whatever the answer is, and it turns out to be D. Number 11. Same thing, very straightforward question. You're given the velocity. You're given the frequency. As a matter of fact, I don't know why this question appears on the test. It's identical to the other question. Simply divide those two and you will get the answer, which is 1.07 meters. Okay, we're cruising now. Question 12 is a little more tricky. You generate a wave. So this is similar to that question 9 that we did. You generate a wave in a spring stretched out on the floor by oscillating your hand back and forth at a frequency of 2.8 hertz. The wave has a wavelength. Okay, so this one's good because they've given you the information in terms of wavelength and frequency. So for this question, I'm going to use the universal wave equation because that's the way the information is presented to me. If the wave takes 3.7 seconds to travel to the other end of the spring, what is the length of the stretched spring? So this is very similar to 9. They're just asking you for the length of the stretched spring. So that's what they're asking. And it takes 3.7 seconds to go there and back. That's really important. It takes 3.7 seconds to travel to the other end of the spring and back to your hand. What is the length of the spring? So if I'm working on this question backwards, then V equals D over T, I'm looking for D. I'm looking for the distance that it travels. What is the length of the spring? The distance it traveled there and back. And then I'm gonna have to use some common sense to determine how long the spring is actually stretched to. What do I have? Well, I have the frequency and I have the wavelength, therefore I can calculate the velocity. So the velocity of the wave turns out to be 5.32. And now I'm going to go to this part right here and calculate the distance that it travels. But you have to think about this carefully. So that's the velocity of the wave. As it travels, the pulse as it travels is going at 5.23 meters per second. 5.32 meters per second. The question is asking for the length of the spring. So all we want is this length, and it told us that it took 3.7 seconds to go there and back. So what am I going to use for the time? I'm not going to use 3.7 seconds because that's how long, that's the distance in that time it traveled 2 lengths of the spring. So I'm going to take that number and divide it by 2. Right, because that's how long it took to travel 1 length of the spring, and all I want is the length of the spring, and that will So you'll end up getting an answer of 9.8. B. Number 13. Oh, a classic ratio question. Good. And this is not a terribly difficult one. We've got the ultrasound system for medical use has a frequency of 12 megahertz. Capital M is mega, small m is milli. When it passes through bone, the speed of the ultrasound is 3.5 times 10 to the third. When it passes through muscle, the wavelength is 1.23. What is the ratio of the speed of the ultrasound in bone compared to its speed in muscle? All right, so we want the ratio of the speed. Speed equals wavelength times the frequency, frequency times wavelength, whichever you want. So what we need here is the wavelength and the frequency. Oh, wait a minute, what is the ratio? Oh no, this is made even easy for us because it gives us one of the speeds. We want the ratio of the speed in bone compared to the velocity in muscle. And it's given us the speed in bone, which is 3.5 times 10 to the 3. All we need to do is calculate the speed in muscle. And it tells us we've got the frequency here. We've got the wavelength here. Therefore, we can calculate the velocity by simply we can multiply those two numbers together. If we multiply those two numbers together, we're going to get the velocity of the ultrasound in muscle. And that turns out to be, oh, don't forget this though. Let's do this neatly. Velocity equals wavelength 1.32 10 to the negative 4, 12 times 10 to the 6. Don't forget it's megahertz. So you got to put times 10 to the 6, and you multiply those two numbers together, and you end up getting 1584. And then once you divide those, you're going to get 2.21. Your answer is C. Okay, we've got a few questions related to this diagram here. The number of wavelengths in this diagram, you better get that one. One wavelength. Two wavelengths. Two. Which of the following sets of points indicates the position of antinodes? Okay, so let's just review antinodes and nodes. So the nodes are where complete destructive destructive inference. How many nodes are there in this diagram? Put them in blue. 1, 2, 3, 4, 5. There are 5 nodes. That's where a crest meets a trough, and they have complete destructive interference. So the wave gets cancels out, and it doesn't appear to be moving in those positions. The antinodes are where there's a crest meeting a crest or a trough meeting a trough. So how many are there here? 1, 2, 3, 4. So we have 4 antinodes. And question 15 is saying, which of the following sets of points indicates the position of the antinodes? Oh, okay, that's pretty straightforward. A is A, C, and E. A, C, and E. There you go. That one right there. Easy peasy. The standing wave in this spring has a frequency of 1.24. If the spring is stretched to a length of 3.65, the speed of the wave is Okay, we're gonna have to think about that one carefully also, because if we want to calculate the speed of the wave, we need the frequency times the wavelength. We have the frequency, it's 1.24. Do we have the wavelength? No, but it's easy to calculate because it tells us the string is stretched out to 3.65. So you're going to say, well, if two wavelengths equals 3.65 meters, then one wavelength will equal how much? Well, it will be half of that. So if you want, you can just put 3.65 divided by 2, multiply those numbers together, and you are going to get an answer of 2.26. D, D, D. 17, a wave in a spring. Ooh, this is a good one. A wave in a spring stretched to a length of 7.5 meters travels at that speed. What frequency is required to generate a standing wave pattern with 7 antinodes along the length of a spring? Ooh, you're definitely gonna need a good diagram for that one. 7 antinodes. What frequency? So it's 7.5. So here we go. We start there. I'm gonna draw 7 antinodes. 1, 2, 3, 4, 5, 6, 7. I'm going to label them. 1, 2, 3, 4, 5, 6, 7. And you have to have nodes at both ends. So that's why I went to 7, and then I had to come back down to here, because you must have nodes at both ends. So if you ask how many antinodes are there, 7. How many nodes are there? 8. There's always one more in a fixed spring. There's always one more node than antinode, because you have nodes on both ends. So that's what it looks like. And we want to know the frequency if it's stretched out to 7.5. So this is 7.5 meters. And what you have to ask yourself in this question is, if that's 7.5 meters and contains 7 antinodes, what is one wavelength? So here's one wavelength. That's one wavelength, right? How many meters is that? And the best way to figure this out is to figure out, well, how many wavelengths are there all together in the whole pattern? Well, there's 1, there's 2, there's 3, and there's a half of a wavelength. So in other words, there are 3.5 wavelengths stretched out over the 7.5 meter long spring. And you need to know, to figure out the frequency, you need to know how much is one wavelength, because we're simply going to use the formula. Velocity over wavelength, right? And you've got your velocity. What some people are going to do, they're going to read this question too quickly, and they're not going to think about it, and they're just going to use this as the wavelength. But that's not the wavelength. That's the length of the spring. So make sure you read this question very carefully. And this is the key here. That's 7 antinodes. So I'm just going to do it as a proportion. You can probably figure it out any way you want. You're going to say if 3.5 wavelengths equals 7.5 meters, then how long is what is the length of one wavelength? So if you do that, you end up cross multiplying and dividing, and you get x equals 2.41 meters. And some people would have just said, oh, okay, well, I just have to go 7.5 divided by 3.5, and I'm going to get the answer. And absolutely correct. And we're good. And you end up getting an answer of 1.81 hertz, which is C. Great. That is a good question. Okay, we're at 15 minutes. Let's stop there and then go on to the third part.